Hi, welcome. I'm trying to learn electrical engineering, today thermoelectricity, and after we've done it, we're going to do standing yoga. And if you participate in the standing yoga, then it's been at your own risk. And this is part 4 or 5 that we're reading. We read it already, but we didn't understand it. So we're just trying to read it again. The use of the various equations we have discussed will be clearer if we consider the various aspects of a very simple problem. Consider a 60-watt lamp bulb, one of the kind you most probably use at home, on the mains electricity supply at 240 volt. So we're having 60-watt lamp bulb on the 240 volt electricity main supply. 1. The power used by the lamp is 60 watt. In example, it converts 60 joules of energy, of electrical energy, to heat energy every second. 60 watt means it's converting 60 joules of electrical energy to heat energy every second. In heat units, the lamp produces 60 divided by 4.2, an example, 14.29 calories per second. Okay, to convert into the heat units with 60 watt, which are 60 joules of electrical energy to heat converting per second, would be 60 divided by 4.2 is with the rule. Okay, whatever. Most of this heat appears as heat. The lamp we all know becomes hot in use, but the small part of the energy is radiated as light. Light is in fact merely a special name given to the particular wavelengths of the radiant heat energy to which the human eye is sensitive. Okay, most of it in these lamps is converted just to heat, some of it also in the light. Second, if we now use the expression power in watts equals speed equals I, we can calculate the current I flowing through the lamp. The current is 60, these are the 60 watt, divided by 240, this is the amount of electricity on the main supply, or 1 divided by 4 ampere. How do we come to the 1 divided by 4 ampere? It is clear that 60 divided by 240 is 1 divided by 4, but how would we do it if it's not clear? Okay, suppose we had been told only that the potential difference was 240 volt and the current 1/4 ampere. And not the voltage. We could then have calculated the heat produced per second as follows. So we were only told that 240 volt were on the main supply and that the current was used up as 1/4 ampere. But not that it are 60 watt. Then we could have calculated the heat production equals volt multiplied with the current multiplied with T divided by 4.2 calories. So the 4.2 there seems to be the thing always. Here, it is found where I is the current in amperes, V is the potential difference in volts, and R is the resistance in ohms. Heat is, however, usually measured in calories, a calorie being a unit of heat energy. Mechanical energy is measured in joules. A rate of working of 1 joule per second is indeed what is meant by the term watt. It is found by careful experiment that when mechanical energy is converted into heat energy, 4.2 joules of former produce 1 calorie of latter. Okay, 4.2 mechanical energy making 1 heat energy. And that seems to be independent of whatever what lamp, that's just the case. Mechanical energy, heat energy. Okay, there's the 4.2. Now, the volt multiplied with current multiplied with the time divided by 4.2, or an example, 240 times 1/4 times 1. 1/4 is the current. What is the current? We have 240 volt and 60 watt. How do we come to the 1/4? Okay, well, it's again 40.29. If we now use the expression powers in watts, powers in power in watts equals V times I. We can calculate the current I flowing through the lamp. I equals 6 divided by 240. Or 1/4 ampere. Okay. Whatever. 3. Using the relationship V equals IR, we can calculate the resistance of the lamp. R equals 240 divided by 1/4, in example 960 ohms. Okay, that is the resistance. It is the amount of power divided by the ampere which the lamp is burning up. Yes, so that is the resistance, that makes sense. The amount of power into it and the amount of taking out of it is how much is resisted by going through it. If we had been told only that the lamp had a resistance of 960 ohms and was to be used on a 240 volt main supply, we could still have calculated the heat produced per second. Heat production equals V squared times T divided by 4.2 resistance calories. And these are 240 times 1, that means a second, divided by 4.2 times 960. Why? Because we're having the amount of power into it, which has to be for some reason squared. 1 second long divided by 4.2, that is how much of power is converted in mechanical energy into heat energy, is converted into, so just a 4.2 of it, of a 240 times 240, just a 4.2 of it, times how much is taken out, is now how we know how much is now going in whatever calories. Where I is the current in amperes, V is the potential difference in volts, and R is the resistance in ohms. Heat is, however, usually measured in calories. A calorie being a unit of heat energy. So 14.29 calories of heat energy were produced because we had a power of 240 times 240 for some reason squared for 1 second long, but just 4.2 of it, but it was taken out 960 times for 4.2 of it, which makes 14.29 calories of it. In brief, the situation is this: that any two pieces of information about a lamp or any other electrical appliance tell us all that is to be known. The applied potential difference, the current, the resistance. I have an idea. I annotated in the last part. Why are we talking so much about how to calculate the third part? And I have an idea. What if someone is building something and knows two things and have to now know how big the third part would be, or what to plan for the third part? That would make sense. So if someone we have so and so much main supply, and we have that and that light bulb, how much heat and light would we then produce? So there is something very specific and very useful how to calculate out of two knowing things. The applied potential difference, the current resistance, the power rating, and the rate of heat production, all 5 values can be calculated providing we know just 2 of them. A summary of the various forms of equation which can be used is given in the next chapter, and your teacher will be able to give you practice in using these to do simple calculations. Practical applications. The practical application of the heating effect of a current should be familiar to you. Basically, they all involve passing an electric current through a resistance wire and using the heat so produced. By this stage, you should appreciate that the higher the resistance, the less heat is produced. These 3 situations are used in practice. A fine wire is heated until it becomes white hot and emits light. This is the principle of the incandescent or filament lamp. The filament is made of the metal tungsten, which has a very high melting point. Tungsten is used also in the Large Hadron Collider to catch some type of particles, because it is very dense. And it has a high melting point. Do things have a higher melting point the more denser they are, or the more higher they are on the periodic table? I don't know, it would be interesting. I don't think so. I think I would know it if it would be. Second, a thin wire is heated to red heat so that most of the heat is emitted as radiant heat. This is the principle of the electric radiator of fire and such devices as boiling rings. Kettles and irons usually have elements in them maintained at red heat. So making it the red hot, so that it's making heat. The other one was white hot, emitting light. 3. A very long wire carrying currents are often kept hot but below red heat. Such heating elements are used in electric blankets, in convectors, heaters, and fan heaters. Sometimes the term black heater is used to indicate that the heated wire is at lower temperature than red heat. There is, of course, less fire risk with a black heater than with a radiator with an exposed red hot resistance wire. And the third thing was, something is made hot, that it is carrying, but not that they're actually on fire. The wires used in red and black heaters are of some high resistance alloys such as nichrome. The particular advantage of these alloys is not merely that their resistance, size for size, is high. I was saying it's just a small one that has a big resistance. They don't need a big wire to have a big resistance. But that the resistance does not alter greatly when they become hot. So we can heat it up and they're staying with the same resistance. Some actual values will make this point clear. Tungsten, on the other hand, has a low resistance when cold. Low resistance when cold, which means that an incandescent or filament lamp takes a high current when first switched on. Low resistance when cold. Switched on the lamp, a lot of current. It's taking a lot of high current. But this current becomes much less once the filament is hot. This is not desirable, but the use of other resistance alloys is out of the question, as these would melt before attaining a high enough temperature to become incandescent. What does incandescent even mean? The word seems to mean something. Is it another form of glowing? Another word for glowing? It becomes a white hot. Okay, other things would melt before they attain that point. Therefore, tungsten is used, even though when it is switched on, it uses at the beginning a lot of current. And if someone needs just the light for 10 seconds, it is not efficient. Resistance of 1 meter lengths of 30 standard wire in ohms material. Copper at cold resistance 0.2, red hot 0.9, and it doesn't reach white hot because it melts at 1000 degrees. Constantan, cold 6 resistance, red 6, but it melts. Nichrome 13 resistance when cold, 14 when red hot, but useful up to 1000 degrees, but it doesn't reach white hot. And tungsten, cold at 0.5, red hot 2.4, so copper would be better with 0.9, but tungsten reaches the 8.6 when it is white hot, or whatever would be better. Maybe nichrome would be better, but nichrome is melting or something. And therefore tungsten, because it reaches white hotness at 3000 degrees Celsius and has been a resistance of 8.6. Is that the example? 960 ohms. No, it was not. Okay, that was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. If you stay here, participate in our 1 minute yoga, then it's very clear. Let's go to stand yoga. Feet is in together, believe in the answer. Out and down. In and up. Out up to the side. In and up. Out up to the other side. In and up, make an inch of space between feet, out to the other side. In and up onto the toes. Out up to the other side. In and up. Out and down, lean onto the knees. Breathe in. Out, make a head of the back. In the round back. Out the bend of the back. In middle. Out, come with the round back. Up, make it to top back with shoulder. In the arms up, come up to the toes. Out and down, feet together. Breathe in with the right leg. Out, stretch the left one. In change. Out the right one. In middle. Out, down. Breathe in, right hand up, bend the left knee, look to the sky. In, hand down. Left hand up, bend the right knee, look to the sky. Hand down. Make a hand with space between your feet, shift into the heels, breathe in and down. Out and up. Feet together. Breathe in, half half straight back. Out and down. In half half straight back. Out and down. Breathe the arms up. Lean back, draw the shoulder blades together. In and up into 20 fingers of each side. Out and in front. In and up, change feet intertwining. Out and in front. In and up. Out and back with long arms. In and up. Out and down. Breathe the arms up. Bring the hands to touch a little bit down to the heart center. It was for 100 seconds. Send yoga. Thank you very much. That's the next time.